In this lecture, we are going to talk about another problem, how to find duplicates in a given array. So the problem is that we want to find duplicates in an array of integers in linear running time complexity, where the integer values within this array are smaller than the length of the array. There are several approaches to solve this issue. First of all, we can use the brute force approach, which means comparing all the items with all the rest, but it has ordo n squared, so quadratic running time. We can do better. For example, we can use hash maps. So we just have to traverse the given array and consider all the items one by one and try to insert each item in a hash table with the value as the key. If you cannot insert the item, it means that it is a duplicate. So this approach is quite good, but there's a problem that it is not an in-place algorithm. We can do better than this. So the third approach is to use absolute values. With this approach, we can achieve ordo n linear running time that is in place as well. So this is what we are going to consider. Okay, so first of all, we have an array of integers. This array is called capital T. So first we have to consider all the I items of the array T, and we have to check the sign of the T absolute value of T with the index I. So this I is going to be the index of the given items as far as this array is concerned. So we are going to iterate through all the items of the array, and we just have to check the sign of this entity. So the array with the index absolute value of the array at the I index. So the value within the array is going to represent an index again, as you can see. And basically we just have to check the sign. If the sign is positive, then we have to flip the sign. Of course, we just have to negate this entity. Anyways, the sign is negative because we have already flipped the sign earlier in one of the previous iterations, so it means that the given item with index I is a repetition. So basically, that's all about the algorithm. Let's take a look at a concrete example. For example, we have a one-dimensional array 2, 3, 1, 2, 4, 3. As you can see, the values within this array have values smaller than the size of the array. So the size of the array is 1, 2, 3, 4, 5, and 6. As you can see, all the values within the array have a value smaller than 6. Okay, so as far as the algorithm is concerned, we just have to iterate through the array and consider all the items one by one. So the first item is 2. We have to check the sign of this entity. So the array with the index absolute value T with index I, in this case the index is equals to 0. The T0 is, as you can see, the value in the first array block, which is 2. So that's why we have to check whether the item in the array with index 2 is positive or negative. The given item with index 2 is 0, 1, 2, so this is the item which has the value 1, which is greater than 0, so the value at that index is positive. It means we have to flip the sign of this T with index 2. So what does it mean? That 1 is going to be transformed into -1. Then in the next iteration, we have to consider the next item in the array. Again, we have to check whether this value is positive or negative. In this case, the I index is 1. The T1 is 3, as you can see. So we have to check the item with index 3, 0, 1, 2, 3. It is 2, it is a positive number, which means that we have to flip the sign of the T with index 3. So 2 will be transformed into -2. Okay, in the next iteration, we have to consider the next item. So again, we have to check whether this entity is positive or negative. What's extremely important that we have to use the absolute value. So the T index 2 is going to be -1, but we have to use the absolute value. That's why it is going to be +1. The item with index 1 is +3, which is a positive number. So again, we just have to flip the sign Okay, let's consider the next item. In this case, the I index is 3. 0, 1, 2, 3 has the value -2, but we are dealing with the absolute value. That's why we have to check the item with index 2. 0, 1, 2 has the value -1, which is a negative value. It means that the given item we are considering at the moment, so with the yellow color, is a repetition. As you can see, because we have already considered 2, we have found a given repetition. So far we know that number 2 is a duplicate number in this one-dimensional array. Okay, let's keep going. We have to check where the I index is equals to 4. The array value with index 4 is equals to 4, which is positive, so we just have to flip the sign. So +4 will be transformed into -4, and we have to consider the last item. So t with index I equals to 5, it is going to be the item with index 3. 0, 1, 2, 3 has the value -2, which is smaller than 0, so we know again that there is a repetition. So we came to the conclusion that there are several duplicates in this one-dimensional array. To be exact, the number 2 and number 3 are repetitions. So this is how we can check duplicates in a one-dimensional array in linear running time complexity. As you can see, we just have to traverse the whole array once, which means that we consider every single item on a one-by-one basis exactly once. So this is why it is a linear running time complexity algorithm without the need for extra memory. So it is an in-place algorithm, very efficient. So this is how we find duplicates in an array in linear running time complexity. So let's consider the concrete implementation. We create a function, find duplicates, and we define the list data structure here. So what do we have to do? We have to iterate through on a one-by-one basis as far as this given data structure is concerned. So basically, if we have a list 1, 2, 3, and 4, for example, then what's going to happen? In the first iteration, we consider the first item. In the next iteration, we consider the next item, the third item, fourth item, and so on. And what do we have to do? We have to check that if the nums with index num, so basically it is the same as we define a given index, and then we get the nums with index I. Of course, in this case in Python it is quite convenient because we can consider the item itself, which means that we can use something like this. Of course, we have to use the absolute value of that given num. And of course, if it is greater or equals to 0, then we have to set nums with absolute value num to be equals to minus nums with absolute value num. Else, we know for certain that we have found a duplicate. So we print out that repetition found, and for example, we append the string format of the number, and we have to use the absolute value as well. So let's see whether it is working fine. If we have the main functions, something like this as usual, what do we have to do? We have to define a list data structure 2, 6, 5, 1, 4, 3, and 2. And let's call the find duplicates function with n as the underlying list data structure. So of course, as you can see, there are duplicates as far as the value 2 is concerned. What's absolutely crucial, that this method cannot handle values smaller than 0. It is absolutely crucial. Of course, if we use, for example, -5, or for example, we have -10 here, then the absolute value of the given number, for example, -10, is equals to 10, and 10 as the index will be resulted in an index out of bound exception. So of course, this method is going to work fine when all the items have values greater than 0. Okay, so if we have the values like this, then repetition found with value 2. And by the way, it is absolutely crucial that the maximum item is smaller than the size of the list, so the number of items. Of course, we have 10. Then again, what's going to happen? We convert the absolute value of the number into 10, and 10 as an index is outside of the scope of this list, so we will get a list index out of range error. So this is why we have to make sure that the values are going to be fine, but anyways, it is going to work just fine. Okay, so this is how we can find duplicates in a given list data structure in linear running time complexity. As you can see, we just have to consider the item once. So we can achieve ordo n linear running time, of course, where n is equals to the number of items in the data structure. So this is how we can implement this problem. Thanks for watching.